Hello dear IPE students, welcome back to NEET World, and this is our session 2 on IPE examination discussion. Okay, particularly we will be discussing chemistry subject here. Okay, and this is our session 2, and in the first session I have given the perfect strategy, I mean what to study and where you can get the complete notes and all, and I also started discussing important questions right now. So in the first session itself I have covered one LAQ type question from structure of atom, that is especially we can say Bohr's atomic model. We know that will be definitely a very important question for IPE examination, right? So now just look at this, what are the important questions we have from first chapter? We have, these are the chapters from which we can expect a 8 marks question right now. So from structure of atom we can have, from structure of atom we have only 2 questions to be focused more and more clearly. One is Bohr's atomic model and second question is quantum numbers right now. So in this session I will be explaining the second question, that is quantum numbers, and this is for your information. I have covered the first question, that is Bohr's atomic model, in the first session. If you haven't watched it, just go and watch the session 1 video after this live discussion, okay, so that you will definitely get one 8 marks question in your final exam from this structure of atom, and you are going to write it without having any confusions. And one more thing guys, you might be not having the study material also. See, what I'm going to give here is, just look at this book here once, the booklet here which I am showing here on the screen. Just look at this book. So this is our NEET World C60 out of 60 book material, that is for IPE exam, specially designed for IPE exam. So this book contains very important questions along with blueprints, sample papers, previous year papers, guest papers. Okay, so now you can finish this in the time that you have for your exam preparation. Okay, right. So here this is the about the book, and this is our index paper, and now this is a blueprint where you can expect 8 marks question from which topics. This thing we already discussed. Okay, now you can use this book or this material, this booklet which are made by this NEET World Institute only. Okay, so now you can use this material. I am going to explain line by line given in this book, so that you can read the book as well as you can listen to me, so that you will get complete clarity and you are ready to write in the exam also. Okay, so just attend the live session till the end, so that you will get complete clarity on our discussion. At the end you just write it in a pen paper, you just take a paper and try to write it in that. Therefore everything will be there in your mind. Okay, these are very short answer type questions. Now we are going to discuss very long answers, I mean LAQ type question. These are short answers. We are covering everything from this book, no issues about that. So now let me show you this first. So this is about the book which I am going to show here first. In the long answers we have finished this discussion, like postulates, Bohr's atomic model and its postulates right now. So this discussion is completed in the last session. I hope it is clearly visible. If not, just mention in the chat box. Yeah, so I hope it is clearly visible. If not, let me zoom it out. Yeah, so now it is clear now, right? So look at this. What are the postulates of Bohr's model of hydrogen atom? Discuss the importance of this model, explaining line spectra of hydrogen atom. So this is how the question will be given in the exam, and these are the postulates that we have discussed in the last class. So I do not want to discuss the same thing again. So now you need to write in this manner, you need to express your answer in this way, and you know these are the importance of Bohr's atomic model. So now what is our second question here? So how are quantum numbers N, L, M, L, Ms are arrived, and what is the significance and significance or importance of these quantum numbers will be one more important question you must be focused here. So now what is the use of quantum numbers? First of all, so quantum numbers wala use enti? So this is a generalized question first, just make it yourself. See, quantum numbers gives the exact address of an electron present in an atom. So where an electron is present in an atom, so it will give the position or exact address of electron present in an atom. See, to describe the position and energy of an electron in an atom, 4 quantum numbers are given here. So what are the 4 quantum numbers here? So one is a principal quantum number, next azimuthal quantum number, next azimuthal quantum number, next this one angular magnetic quantum number and spin quantum number. These are 4 things. See, this principal quantum number and next azimuthal quantum number is there now, also called as angular quantum number. So first of all you need to know what are the list of quantum numbers. One is a principal, angular, magnetic, and the next is spin quantum number. These are 4. Okay. So now what is the use of this each and every quantum number? First of all let us understand. So each quantum number gives a specific information about electron. ప్రతి ఒక్క క్వాంటం నెంబర్ కూడా ఒక పర్టికులర్ ఇన్ఫర్మేషన్ ఇస్తుంది, ఎలక్ట్రాన్ యొక్క ఇన్ఫర్మేషన్ ఇస్తుంది. ఫర్ ఎగ్జాంపుల్, you are staying at your home, so how do you give your address? So I belongs to some particular state and particular district and particular mandal or village, like that we will be giving, and home address like your home number, like house number, like 1-20 something like that. So similar here we have 4 quantum numbers. Each quantum number describes a particular information about the electron. So the first number here is principal quantum number. So this principal quantum number indicated with symbol n, small n. So now this is proposed by Niels Bohr. Who proposed principal quantum number? Niels Bohr. So whatever I am showing here, so just make the note of it and you can read it and you can ready to write your exam also. Okay, if you want you can add few more points to make it a little bigger and more more clear way to express. See this quantum number, this principal quantum number, n values varies from 1 to n. I mean it goes from 1, 2, 3, 4 so on n till n, or we can also represent them with letters k, l, m, n so on like that. Okay, so now the maximum number of electrons in a shell is given as 2n square. So what exactly it means? See, here if I have a nucleus, now what I am doing here, around which I just want to mention it like this. So what is this circular path or whatever it is? So what it is representing? So it is representing our principal quantum number n. Okay, so what is this principal quantum number n? So now n number equals to 1 here, and second orbital here, orbit I am writing here, n equals to 2, like this we can represent. So this n 1, 2, 3 so on indicates what? Principal quantum numbers. Okay, so now what is the use of this principal quantum number? See, as n value is increasing, see n equals to 1 here, n equals to 2 here. So as n value is increasing, distance from the nucleus to outermost shell also increasing. So distance is increasing now. So radius, this is r1 and this is r2 I am saying. Now r2 is greater than r1. So now principal quantum number helps in giving its radius also. It describes the size. So as radius, this is radius increasing, that is nothing but size is increases as your principal quantum number value increases. And one more thing, if electron present in first energy shell, it will be having lower energy, and if it is having in second quantum number n equals to 2, second shell, it will be having little more higher energy, like that. As n value increases, its energy also increases. The electron present in that nth shell also increases, energy of that nth shell electron also increases as its n value increases. Okay, so now what it says, so it describes what is the significance of principal quantum number. It describes the size and energy of the orbital. Okay, these are the 2 points to be remembered. Now in a particular shell, how many electrons we can fill? So that can be given using this particular formula. So what is this n indicates here? It's a principal quantum number. For example, n equals to 1 if I take, you can fill maximum of 2 into 1 square, that is maximum of 2 electrons can be filled here. So how do you fill the 2 electrons? See, n equals to 1 means we have 1s orbital. Okay, I will tell you how this 1s we are writing later. So now one orbital can accommodate only 2 electrons maximum, those are these 2 electrons. If n equals to 2, so n equals to 2 means 2 into n square you are writing now. So 2 into 2 square 4. Okay, so you got 8 electrons you can fill in this shell. Okay, so now in an nth shell, what I am saying, in an nth level, that is principal quantum number n equals to 2, n equals to 1, like that we are writing now. So in an nth level, how many orbitals are present? How many orbitals? Number of orbitals equals to n square. What I am writing? N square. For example, n equals to 1, so your number of orbitals will be 1. If n equals to 2, number of orbitals will be 4. Okay, so in one orbital we can fill 2 electrons. Therefore, how many orbitals we got in second energy level? 4. So 4 2s are 8. So maximum of 8 electrons we can fill in a second energy level, like that. So as n number increases, energy increases. Remember these 3 points that whatever we have discussed now. Okay, so once again look into it. Principal quantum number indicated with n, and it is given by Niels Bohr. It varies from 1, 2, 3, so on, it will be goes on. Okay, or you can indicate with KLMN, so on also. Okay, next. So maximum number of electrons in a shell is given as 2n square. Next, it describes size or radius and energy of orbitals. Remember this. Next, along with this, just look at this second quantum number here we have is azimuthal quantum number. So what is that? Azimuthal quantum number. Okay, so azimuthal quantum numbers helps in determining the shape of orbital, or it describes the shape of orbitals. What I am saying, azimuthal quantum number describe the shape of orbital. This is indicated with symbol I and it is given by Sommerfeld. So who proposed this? Sommerfeld. Okay, and values of azimuthal quantum number I varies from 0, 1, 2, so on, n minus 1. So from where to where it goes on? So it will be starts from 0 and goes on till n minus 1. So what do we mean by n minus 1? See, if principal quantum number is something like 4, so L value can varies from 0, 1, 2, 3, up to 3. Why I am writing only up to 3? So because it should be varies only from 0 to n minus 1. N value is 4, so 4 minus 1 is 3. So up to here we can say. Okay, so now each of these 0, 1, 2, 3 have some particular indication. For example, if I say 0, L value is 0, it indicates S subshell. What I am saying, it indicates S subshell. So what it is? It represents subshells in the main shell. See, what we studied now, there is a nucleus. Around nucleus there will be shells like this. Okay, so in these shells there will be again subshells. First of all we have studied about shells. Now we are studying about subshells. So now what are the subshells we have? If n equals to 1, the possible subshell will be up to 0 to n minus 1 only now. So n minus 1, that is 1 minus 1 is 0 only. So in first shell you have only 0, that means S subshell will be present. Only one subshell, that is S. Okay, in second shell n equals to 2, so you can have L equals to 0 and 1. Okay, so what are the subshell possible? If it is 0 value, L equals to 0 means S subshell. If L equals to 1 means P subshell. So in the second shell you have S subshell and P subshell. What we have? One S subshell and one P subshell. Okay, and along with this thing, so in each subshell there will be orbital. What I am saying, in each subshell there will be orbitals. Okay, so what do we mean by orbital? This is the maximum probability of finding an electron in the 3-dimensional region around the nucleus. Okay, so what do we mean by orbital? See, if this is a nucleus, around this nucleus, the maximum probability of finding an electron will be there now, the region around the nucleus where we can have maximum probability to find an electron is called an orbital. Okay, so in the orbital only we have electrons, that's it. Okay, so now what are the orbitals possible for S subshell? So it depends on its L value. Here we are saying 0 now, so you just take 2L plus 1 indicates number of orbitals in a given shell. So how much L value we have here for S? It is 0, no? So 2 into 0 plus 1. So you will get 1 orbital. So in S subshell, how many orbitals are there? 1 orbital will be there. So in P subshell, in P subshell, how many orbitals will be there? So in P subshell, L value is how much for P? It is 1. So 2 into 1 plus 1. So there will be 3 P subshells. So what are those? Px, Py, Pz. Px, Py, Pz. Like that, if you take one more L equals to 3, so what are the possible things we have? So you just take what are the possible orbitals here. So 2L plus 1 we are saying, 2L plus 1. So 2 to the 4, like if I take this 2 value here, 2 to the 4 plus 1, 5. So that's way we are saying for S orbital, for S subshell we have 1 orbital only. For P subshell you are saying there are 3 orbitals. In D subshell there will be 5 orbitals. In F subshell there will be 7 orbitals. Why 7? So 2 3s are 6 plus 1 7. So that's why we are giving the number of orbitals will be different for different subshells. Okay, hope whatever we are discussing is clear. Right. Next thing is here, see, look at this box. For each subshell there will be some shape. Okay. So for S subshell, what is the shape? Spherical. You need to remember this. Okay. So for P, spherical means it is around the nucleus, it will be in spherical form. See, around the nucleus, if I say S subshell, around the nucleus it will be spherical form. Okay, just like take like a sphere, at the center we have nucleus, around that we have spherical shape. Okay, that is for S orbital. Next, when it comes to P, it looks like a dumbbell, like this. Okay, positive lobe with a negative lobe down. Okay, and here for double dumbbell is for D orbital. So just represent them like this. This is one dumbbell and this is another dumbbell. So like a double dumbbell for D orbital. Okay. See, there are angular momentum quantum L values are varying here. Okay. So 0, 1, 2, 3 like that we are writing. Okay. So that's it. So for S subshell, what is the L value we got? 0. For P subshell we are writing L equals to 1. For D subshell we are writing L equals to 2. For F subshell we are writing L equals to 3. So now number of S orbitals are how many? So 2L plus 1. So 2L plus 1. If L is 0, this becomes 1 S orbital only. And this 2 into 1 plus 1 now. So you are getting 3 P orbitals. What are those P orbitals? Px, Py, Pz. Okay, Px, Py, Pz. That's why whenever we are writing electronic configuration of P orbitals, we are making it as 3 boxes, like each orbital represented by 1 box here. Okay, and each box can accommodate 2 electrons like this. Okay, right. That filling will follows Bohr principle or Pauli's exclusion principle, Thomson rule. I hope you know that. Next, if L value is 2, then you can fill it as 2 to the 4 plus 1. So you are going to get 5. So what are these 5 d orbitals? 5 d orbitals are what? dxy, dxy, dxz, dyz, and dx square y square, dz square. These are the 5 d orbitals possible here. And what about L equals to 3? There will be 7 f orbitals possible. Okay, and it will be having a complex shape that we cannot represent here on the 2-dimensional sheet. Okay, right. Next, what is the third quantum number? So just take these points, make it a note, and you just go through the notes once again. That's it. Okay. Next, what about this? What is our third point here? magnetic quantum number indicated with the symbol ml. See, this one I told you, this one, first one, principal quantum number indicated with symbol, principal quantum number indicated with symbol n, okay, and next azimuthal quantum numbers indicated with symbol L, and the next magnetic quantum number indicated with symbol ml. Okay, these are the ways you can remember. So this says about shell and this says about subshell. Okay, so look at this, it is proposed by Landay, it is indicated with symbol ml. The values of magnetic quantum number varies from minus L to plus L. So minus L, next like that, minus L to 0 plus L. So for example, if I say L equals to 1, so if L equals to 1, what we are saying, this is p orbital, we are saying L equals to 1 means. If L equals to 1, how many orbitals are possible? You are saying 2L plus 1, using the formula number of possible orbital, number of orbitals here are 2L plus 1. So now what are those? If L equals to 1, you will get 3 right now. So what are these 3? So that is nothing but minus L, so L equals to 1 now. So now ml values will be, now tell me, minus L, 0 to the plus L, minus L to plus L, like this. So that is nothing but we are saying px, py, pz, px, py, pz. Are you representing this px, py, pz format, or minus 1, 0, plus 1 for these 3 p orbitals. Similarly, you tell me for d orbital L equals to, for d orbital L equals to 2. If L equals to 2, tell me what are the possible orbitals we have. So if L equals to 2, so 2L plus 1, number of subshells will be, number of orbitals will be 2L plus 1. So 2L plus 1 is how much? 2 to the 4 plus 1, 5. So what are these? dxy, dxz, dyz, dx square y square, dz square. These are the 5 d orbitals possible when L equals to 2. Okay, right. Now you are saying, now see, minus L0 plus L, see what is the use here again. So it represents orientation of orbitals in the space, how they are oriented in the space, how in the 3-dimensional space, how these orbitals are oriented is given by this magnetic quantum number ml. Okay, so for S subshell, the magnetic quantum number values, ml values possible here is, see this is not I, this is L. This should be L, wherever you are seeing I, just convert it into L. So for S subshell we have L equals to 0 now, so ml value is 0. Okay, for P subshell we are writing L equals to 1, so ml values will be minus L to plus L we can write. So what are the minus L here? Minus 1, 0, because 0, minus L to plus L means in between we have a 0, 0 and plus L. So when L value is equals to 2, that is for d orbital, so what are the possible numbers here? Minus 2, minus 1, 0, plus 1, plus 2. So that is why we got these numbers here, so which are plus 2 here. So which are how many? 1, 2, 3, 4, 5. So 5. How do we got this 5? Because it is varying from minus 2 to plus 2. So these are nothing but each orbital indication. For example, you are saying the number of orbitals equals to 2L plus 1. So 2L plus 1 is nothing but number of orbitals means 2 to the 4 plus 1, 5. So 4 plus 1, 5. So 5, how can you indicate them? In 3 boxes, 5 boxes here. Okay, so each box is indicated like dxy, dyz, okay, dzx, dx square y square, dz square. Like this we are indicating while writing the electronic configuration. Okay, and for principal like f orbital, what is the L value we have? 3. So it possible numbers are from where to where? Minus 3, minus 2, minus 1, 0, plus 1, plus 2, plus 3, like this. These are the possible ml values for a given particular L value. Next, one last quantum number here we have is spin quantum number. So what is the use of this spin quantum number? See, So it says about the spin of electron. What it says? It says about spin of electron, how electron is spinning. Okay. So now see here, it is proposed by Uhlenbeck and Goldsmith. Okay. And the values are like minus half and plus half, minus half and plus half. So now what is the significance? It explains the direction of electron spin. See, there are two possible spins for electron. Okay. We are indicating as clockwise and anti-clockwise, like plus half and minus half. Okay. If clockwise I am indicating like plus half, I am indicating with plus half, then anti-clockwise will be indicated with minus half. Okay, like that. So electron, each electron there are two possible spins, one is clockwise, other one is anti-clockwise. Okay, it is given by spin quantum numbers proposed by Uhlenbeck and Goldsmith. Next, what he says, it has two values, plus half and minus half. Okay. So now plus half if it is for clockwise, then minus half is for anti-clockwise. Now what is the significance of this principle, like this one, spin quantum number? It explains the direction of electron spin. So it is on the basis of Pauli's exclusion principle. So what is Pauli's exclusion principle? No two electrons have all no two electrons have same quantum numbers. It means there should be at least one quantum number must be differ for any two electrons in an atom. Okay, if you take an atom, for example, I am taking carbon. How do you write the electronic configuration? Atomic number is 6 now. So you are writing 1s2, 2s2, 2p, 2 you are writing. So now if you take any of this electron, none of them are having all four same quantum numbers. At least one quantum number must be differ. So for example, here I am taking p orbital electron. See, you are writing here 1, 2, like this we are writing 1, 2. So now here, what is n value here? For both of them n is 2 only. What about L value? See here it is minus 1, 0 plus 1 if I write. So you got minus 1 for first electron and 0 for second electron, like that. So but no two electrons should have all four same quantum numbers, or at least one must be differ, you should understand that. Okay. So if sometimes what happens, electron will present in the same orbital right now. So like this, if electron is present in the same orbital, see what is the difference in these two electrons? One is having plus half direction, clockwise direction, other electron will be having anti-clockwise direction. So any of the quantum number must be different for two electrons in an atom. Okay. So this is about the quantum numbers here. Okay. Hope complete discussion is clear. So what we have discussed here till now, I just given the discussion on quantum numbers. So what is the use of quantum numbers? It gives the address, exact address, the position of electron. Okay, it gives or explains about position of electron. So the first quantum number is principal quantum number indicated with symbol n. So n says about shell number. Okay, shell number. Okay, after knowing this shell number, so this shell number also useful for finding its energy and finding its size, finding the electron, like energy in which electron is present, energy of shell in which electron is present, and finding the size of the shell in which that electron is present. Next, after this we have subshell, that is indicated with symbol L. Azimuthal quantum number gives about information about subshell. Okay, it is something like knowing your state, then knowing your district, something like that. Okay. So first shell number, next subshell. Okay. After this we have orientation of these subshells. Orientation of these subshells. After this, in this subshell, electron present now, what is the spin of that electron? So these are the four quantum numbers describing about electron position. Okay, you need to remember this because these are the two questions, like one is Bohr's model, another one is this quantum numbers. These are the two questions must be focused for your IPE first year. Okay, right. Okay, now one more thing here. Just a minute. everything is clear. Now, in the first class I have explained, in the first session I have explained about postulates of Bohr's atomic model. Okay. Now, along with that I have given limitations and all. Now, the same question they may make little difference. See here, they may give, see what are the postulates of Bohr's model of hydrogen atom. Same question as like before, that first question as like first question. Write its main limitation, limitations also discussed. Okay, and now they are adding little more thing here. See, also give any two differences between emission spectrum and absorption spectrum. So, this is the extra line they have added in this question when we relate it to the previous question. Okay, in the last class I have explained its postulates, and the next its main limitations also we discussed. Okay, now you can take the same information here. So, now I just wanted to explain you about emission spectrum and absorption spectrum, this because this is the extra part added into the question now. So, how you can understand this? See, there are like two main differences we have, you can understand this between emission spectrum and absorption spectrum. Just imagine there is a photographic plate over here. So, now here I have atom. Okay. So, here we have atom. So, now what I am saying is we are sending some energy to this atom. What I am saying, some light is falling on this atom. Okay, now what it will do, it will absorb some energy, and that if it is absorbing the energy, what happens to its energy is gained now. So, now it will be excites to higher energy state. What I am saying, it will excites to higher energy state. Now see, every species requires suitable amount of energy, some particular amount of energy for their excitation process. Now what I am doing, I have passed some light over here, only some specific amount of energy is absorbed and remaining amount of energy is not absorbed, that is simply going like this. Okay. Now whatever the extra energy, that whatever the remaining energy except that absorbed energy will fall onto this photographic plate. Okay. What happens, that fall onto this photographic plate. Now on this photographic plate you will be seeing complete brightness, but you might be having some missing lines, like some missing dark lines. Why that dark lines are formed? Because at the dark line whatever the light should fall, that is already absorbed by the atom. So that is why that lines are missing on this photographic plate. So how this photographic plate is seems to be, so on a bright background there will be dark lines are seen here. So just read this. Absorption spectrum is produced when electron gain energy, atom gain energy. So in that case what happens, electron jumps to higher energy level from this lower energy state. So now by absorbing the energy only it is jumping into the higher energy level Now this shows dark lines at a specific wavelengths and a continuous bright background. See, on this photographic plate there will be continuous bright background because this light is falling on the background completely, but only some lines, some light is particular wavelength is missing because that is absorbed by this atom. Therefore, its electron is jumping from lower energy state to higher energy state. Whatever the energy absorbed by this, those lines will miss on this photographic plate, which will be resulting in dark lines and a bright background. That is it. Okay, this is a simple way you can understand. Now, when it comes to emission spectrum, it will be somewhat opposite to the absorption spectrum. See, now look at here, again same photographic plate here we are taking. Now here atom is there in its excited state, or electron of an atom is there in this excited state. Electron of an atom is in excited state, and I am saying this is its ground state or lower energy state. Now consider if this electron is falling from this lower energy state, higher energy state to this lower energy state, or it is going excited and coming back to its original state. When it is coming back to its original state, what happens? It releases some energy now. So whatever the released energy that falls onto this photographic plate, what I am saying, when an excited electron falling into its ground state, it will release some energy. That released energy will fall onto this photographic plate. Now there is no extra energy. What I am saying, whatever the energy this excited state electron is having, when it is falling into its original ground state, or lower energy state, the amount which is greater here, na, that will be released. Only that lines, that bright lines will fall onto this photographic plate. Normally photographic plate is dark. On the dark photographic plate you will get some bright lines now. So on dark background you will be having bright lines, in which case in emission spectrum. Okay. So now see, this emission spectrum is produced when atom lose energy. See, when atom lose energy, that electron falls to lower levels. So electron falls to lower levels. When it is falling into the lower level, shows bright lines at specific wavelengths on a dark background. Because why? Because there is no other light, that's why this photographic plate is dark, on which this a bright line will falls. That will be having a suitable frequency or wavelength range, no? So only that line will be appears to be bright, remaining everything is dark. But here that missing lines will be dark, remaining everything is bright. So something like absorption spectra, emission spectrum are complementary to each other. So these are the things to be written in the exam. So understand this. I hope you got complete concept. Now you just like make a note of these 2 points, and I hope you got the complete concept also, that you can use it to write directly without by hearding anything. Okay. And the next here, yes sir, hello, yes, hi dear in the chat box, hello sir. Emission spectrum and absorption spectrum, I hope clear, the discussion is clear about this. Now we will be seeing something regarding the second chapter, that is classification of elements. So now what are the questions to be studied from classification of elements? Tell me first of all. Okay, first one is, it's like periodic properties. What are the periodic properties we have, and how, and what are the factors affecting these periodic properties? Okay, for example, ionization energy is there. So how can you define this ionization energy? So these kind of questions you can expect first, and after this comparison between two different ionization energies like IE1, IE2. These are the two important questions you need to focus, along with one more question, that is write about SPDF blocks. These are the 3 questions you can expect. Any of these 3 you may expect 1 question. Okay, right. Look at this. What is a periodic property? How do the following vary in a group and in a period? So now these are the 4 periodic properties they are saying. How do they vary, they are asking. First of all, define the periodic property means, it means the repetition of properties of elements at regular intervals in a periodic table. In the periodic table is called a periodic property. So what they are saying, the repetition of properties, there are some properties that will repeat in a regular interval. It means from going from 1 to 18, after that 18 again it will repeat. When again it is coming to 1 back, that will be repeating again. Periodic property will be repeats. Okay, it means, for example, I am writing see, we know in periodic table we have S block, D block, P block, and at the bottom we have F block right now. So now if we move from like left side to right side, there are some properties observed, the repetition in their property. I mean, for example, atomic radius, it means the size of elements. If you go from left side to right side, what happens? Size is decreasing. Okay, size is decreasing. So whether it can be a second period, third period, like that. If you go from left side to right side, what happening? Size is getting decreased. So that is what repetition in their properties. See, at the regular intervals, after completion of every 18th element in each period, again this new element is having same trend. Okay, like that. So now see, first periodic property mentioned as per the question is, so see, that is atomic radius here. So why this periodic trends are observed, this repetition is observed here. It occurs because of repetition of similar valency shell electronic configuration at regular intervals. See, if you take any group elements, for example, all alkali metals will be having same general electronic configuration like NS1 you are seeing, and for next element, for alkaline eighth metal it is NS2. Whatever the element you are taking here, all of them are having same general electronic configuration. For example, here you can take beryllium, magnesium, okay, and calcium. If you observe the electronic configuration like 2s2, here 3s2, here it is 4s2, something like this. See, all of them are having same general electronic configuration. Only this n value is changing. This n value is changing is nothing but principal quantum number we studied while studying quantum numbers. So if that principal quantum number is changing, what happens, tell me? What happens, tell me? See, if this is nucleus, okay, around we have electrons. See, if this principal quantum number, here I am taking 1, here I am taking 2. So as principal quantum number increasing, what happens to the size? Increases. So down the group in the periodic table, down the group, their size increases. Why it is increasing? Because their n value here, principal quantum number is increased. Okay, principal quantum number is increased. It means here atomic number is 4, here it is 12, here it is 20. So down the group atomic number is increased in some random way. I mean 4, 12, 20, like that we have. So number of protons are increasing, number of electrons also increases. When I say atomic number is 4, there will be 4 electrons and 4 nucleus, right, protons right now. So now in the nucleus there will be 4 protons in this case. Here it will be 12 and here 20, 20. Okay. So now see, there will be 20 electrons, here only 12. So whatever the new electrons are coming, like extra 8 electrons are coming, no? So those slowly goes to the higher energy levels. So when they are going into the higher energy level, that higher energy level to this nucleus, size like radius, see the distance is increasing now, that is nothing but radius is increased or not. That's way, as down the group if we move, the radius or the size of the atom increases, size of atom of an element increases. Okay. So try to remember this property. So now what I am saying, atomic radius, how do you define this atomic radius? It is simple, it is a distance between nucleus to outermost shell valency electron of an atom. So it is distance between nucleus to outermost valency electron. So distance from the nucleus to outermost shell of an atom is called atomic radius. How does it varies in a group? In a group from top to bottom, the atomic radius increases. Why it is increasing top to bottom? If we move, atomic radius increases, okay, because the new extra electron, the differentiating electrons enters into new shell. See, if I say beryllium, it only stays here, but if I say magnesium, not the 2 valence electrons are coming into this shell. So that's why that differentiating electron enter into higher energy level now. So that's why its radius or size is increasing, that they came into new shell which is far from the nucleus, that's why its size is becoming bigger. Okay, in this way you can understand. Now variation in a period, how it will be varies in period, how it will be varies in a period. So if you are moving from left to right, what happens, the new, see, just take some elements that gives you more clarity, carbon, nitrogen, oxygen, fluorine, like this if you consider. What happens, tell me? From moving from here to here, you just write the electronic configuration. Here you are writing 2s2, 2p2. This is atomic number 6, like 1s2, 2s2, 2p2. Here it will be 2p3 and here it will be 2p4 along with these first things. 2p5, here it will be 2p6. So what is the trend? 2p5 in this case, 2p4 in this case, 2p5 in this case. So what will be the trend you are observing here? That whatever the extra electron is coming, that extra new electron is coming as atomic number is increasing, that is adding into the same shell now. So if it is going into the same shell, whatever the nuclear force increasing in the nucleus, that will attract the this valence electrons towards itself and make the size to be compressed. So now we are moving from left to right in the period of the periodic table, size decreases. What happens to size? Decreases. Okay, atomic size decreases as we move left to right. So variation in a period left to right, atomic radius gradually decreases as atomic number increases. Okay, so as we are moving from left to right, what happens to the size? It is decreases. Okay, remember that. Okay, next. So you need to write in the same manner, like atomic radius, you put the heading and you write these many things, and it is better to give one example for each of this. How does it varies in a group, they are asking, no? So just take first group elements because easy to remember and easy to explain them. See, you just take lithium, sodium, potassium, rubidium and cesium you take. So now what happens, these are the elements present in the first group. Okay, so down the group these are the elements we have. So the bigger sizes for cesium, like this you mention one example, definitely he will impress, and examiner or the person who is correcting your paper will definitely give you the best marks. Okay, and the next, when it comes to period, again take some 2p series elements because most of you are much familiar with second period elements now. What are the second period elements? Lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. Okay, I am not writing noble gases. Why I am not writing? Because noble gases exceptionally having higher atomic radius. That's why I am just ignoring that. I am comparing the other elements here. Okay, because their radius is measured in van der Waals radius. Okay, for this it is not van der Waals. It is either covalent or metallic. Okay, now what I told you, from left to right size decreases. So lithium greater, beryllium, then next boron. Like this is the way you can mention one or two examples, then definitely he will impress and he will give full marks. Okay, right. Next here, ionization energy. So what do we mean by ionization energy? Simply first read the definition, then I will give clear explanation for that. See, the energy required to remove an electron from an isolated gaseous atom. It means, see here, I am writing A is an atom. Okay, so these elements may be in solid, liquid, gaseous state. Right now, first of all, you need to convert that atomic form of that element to its gaseous form. Whether it can be a liquid, solid or anything, it must be taken in terms of gaseous form. So from these, you need to remove one electron. What we need to do? We need to remove one electron. Okay, if we are removing one electron, it will become unipositive cation. So this is the scenario. Okay, now what I am saying, the amount of energy required to remove an electron from neutral, gaseous, isolated atom is called ionization energy. So this is called IE1 because we are removing first electron now. So you should call first ionization energy, and if you are removing electron from this A place, it will become IE2 now because you are removing second electron. So it will becomes IE2, that is A2 plus you can write. Okay, right. Discussion is clear now, whatever we are doing here. Okay, if you remove first electron, first ionization energy. Both if you are removing first and after that second also, it is called as second ionization energy. Okay, right. So once again read the definition. The minimum energy, so if you want you can write the minimum energy required to remove an electron from an isolated gaseous atom is called its ionization energy. Okay, next, how this ionization energy varies in a group. See, ionization energy decreases from from top to bottom in a group in the periodic table. So why it is decreases? See, top elements, let us say lithium, sodium, potassium, rubidium, like this I am taking the elements. This is from a group now. Which group? First group elements. Now if you see, as we go down the group, their size is getting increased, their sizes are getting bigger like this. So if size is bigger, it is easy to remove electron from the valency, right? See, if size is bigger, the nuclear forces on the valency electrons are very less. The nuclear forces on valency electrons are very less, so that this electron can be easily removed out. So if this is a valency shell having electron, the minimum energy required to remove this electron is called ionization energy. So now this removal is easy when it is away from the nucleus. If it is away from the far from the nucleus, that positive charge, the nuclear forces on this electron is very less. If forces are less means you can easily remove. Okay, that's why ionization energy down the group decreases. Why decreases? As down the group atomic radius increases now, it means size is becoming bigger. If size is bigger, it is easier to remove the valence electron. That's one. Okay, so down the group what happens to ionization energy? Decreases. What is the reason? Due to increase in atomic size and shielding effect. Okay, so now what is the example you can take? Say same this one, lithium, sodium, potassium, rubidium, cesium, you can compare. So now what happens? Down the group size is increasing, this is larger size, so lower ionization energy is for cesium. So this will be the order of ionization energy in case of this first group elements. Okay, right. Next, variation in a period. So how this ionization energy varies in a period? Okay, period means like rows you can take from left to right. What happens to the size? What happens to the size from left to right? Decreases now. So if you are going from left to right in a period, second period elements you take first. Second period elements you can take. What are second period elements here? We have lithium, beryllium, boron, carbon, nitrogen, oxygen, like this you take and try to compare what happens here, what happens here. So size is decreasing now from moving from here to there. Okay, smaller size is for fluorine. So now if size is smaller, the nuclear forces are more on the valence electron. It means that valence electron is strongly bind to the nucleus. So if it is strongly bind, the removal of that electron is very difficult. Okay, that's why ionization energy is increasing as we move from left to right. So what I am saying, so ionization energy increases from left to right in a period. Okay, remember this, because in a period the differentiating electron enters into same atomic orbital, that results to decrease in the size, okay, and increasing effective nuclear charge. Okay, because if it is going into the same shell, that nuclear protons also increasing as atomic number increasing, so that nucleus will strongly hold that whatever the valence electrons we are adding, and it is very difficult to remove that valence electron. That's why it is having higher ionization energy as we move from left to right in the periodic table. Okay. Now, if you want to express this with one example, yes, you can do this, but there are some alternations here that also depends on the factors of affecting on ionization energy. So if you express this, yes, this is really well and good, you take these elements only. Now there are some factors like electronic configuration of each element should be considered here. What is the electronic configuration? Here it is 2s1, this is 2s2, and here it is 2s2 2p1, this is 2s2 2p2, okay, this is 2s2 2p3, okay, this is 2s2 2p4, this is 2s2 2p5, like this we are writing. So now since smaller size, more electronegative fluorine atom will be having higher ionization energy. We know as we move from left to right, ionization energy increases. Definitely the one which is at right hand, like left hand side will be lower, right hand side will be higher. So fluorine will be highest ionization energy. After this, between oxygen and nitrogen, if you observe, see nitrogen is having 2p3 electronic configuration. It means it is a half filled p orbital now. So p orbital can accommodate 6 maximum electrons. Now it is having half fill electronic configuration. If it is having half fill electronic configuration, those configurations are highly stable. So energy required to remove from that stable electronic configuration is more, because it is already stable. If I remove electron, it becomes unstable. That's why it is very difficult to remove electron from nitrogen. So between nitrogen and oxygen, nitrogen will be greater than oxygen. Remember this point also. And after this between carbon and boron, so carbon is 2p2, boron is 2p1. So removal of this one electron is easier than this second electron. Okay, so boron here and carbon here. Okay, boron here and carbon. Okay, just sorry, carbon is greater, that is fine, and boron is lesser. Between boron and beryllium you need to compare. Between boron and beryllium, how do you compare? See here it is 2s2, 2s2 s orbital fully filled, and that s orbital is very close to the nucleus. Therefore, I can say penetrating capacity of s is more, that is more closeness to the nucleus is for s orbital. Therefore, it is very difficult to remove electron from this 2s2 electronic configuration. So, electron easily removed from boron compared with beryllium. So, write here beryllium first, then next boron, and least is for our alkali metal, that is a lithium. So, this is the order you can express in your exam, you can mention in your exam, so that really impressive it is. It is enough even if you write up to here, if you give this example it is really good. So, simply remember what happens to ionization energy down the group decreases, as we move from left to right increases, that is it. Okay. Next, what do we mean by electron negativity? Electron negativity means the tendency of an atom to attract shared pair of electrons in a covalently bonded molecule. See here what I am saying, you just take an element A connected with element B with a covalent bond. Okay. So, now depending upon the electronegativity of this A and B, this bond get polarized. So, which side it will be polarized, tell me. See, if I am saying if B is more electronegative atom, means what, that element B is having more tendency to drag the bonded electrons, covalently bonded electrons towards itself. So, now what I am saying, electronegativity means the tendency of an atom to attract the shared pair of electrons in a covalently bond molecule. Okay. So, in this molecule we have a covalent bond. So, this covalent bond electrons are more dragging towards this atom B. Therefore, I can say electronegativity of B is greater than electronegativity of A, that is it. Okay. So, now look at this variation in a group, how this electronegativity varies. Electronegativity decreases down the group. What happens to electronegativity down the group? Decreases. Okay. And this is due to increase in atomic size, because as size increases nuclear attractions decreases. See, if there is small size atom, now what happens is whatever the nuclear forces are there, that will show its effect on valency electrons more effectively and drags them. Okay. If the size is very small, this is the scenario, if the size is very small, that nuclear forces will be effective and attracts the bonded electrons towards itself. But if size is very large, now if size is very large, what happens, this nucleus is here and around it, this nucleus already electrons are present, that is why its size is very big. Now attracting the bonded electrons is very less. So, whenever atomic size increases, whenever having greater atomic size, lower will be the tendency to attract the bonded electrons. Okay. Therefore, I can say it as less electronegative atom. Okay. So, more bigger the size, lower the electronegativity. Okay. Remember this. Okay. Next, how it will be varies in a period. So, electronegativity increases from left to right. So, what happens as we move from left to right, electronegativity increases. Okay. So, it means from lithium to fluorine, if I go, fluorine is highest electronegative element. Okay. So, which is highest electronegative element? Fluorine. Okay. In the periodic table, in complete periodic table, fluorine is highest electronegative element. So, this is about a variation of electronegativity in period. Now, how it will varies in the group? So, it will varies in the group, like group means you just take a vertical column like this. Okay. So, take fluorine, chlorine, bromine, iodine. So, these are the elements of halogen family. So, down the group size increases, now electronegativity decreases. Therefore, fluorine is having larger electronegativity, greater electronegativity than chlorine, bromine, and least is for iodine. So, this is the way you need to express your answer. So, electronegativity down the group decreases and across the period increases, that is it. Next, one more here we have is electron gain enthalpy. So, what do we mean by electron gain enthalpy? The energy change when an electron is added to a neutral gaseous isolated atom. It means It means, see, I have element A, to this I am adding electron. So this element A, first of all, it should be neutral atom and it should be in gaseous state. Okay. So to this element A we are adding electron now, therefore this element A becomes now A minus. Okay, A minus. So the amount of energy whether released or absorbed when an electron is added to this neutral gaseous isolated atom is called its electron gain enthalpy. Okay. So electron gain enthalpy becomes less negative down the group. It means less negative means generally electron gain enthalpy here is negative. What do we mean by negative here? See, if an electron is gained by an atom, it releases some energy. So we can say exothermic process. It can be endothermic also. It depends on element to element. Again, see, halogens, if I say fluorine atom is there, to this if I add electron, it will become fluoride ion. What it will become? Fluoride ion. So this should be atom only and it should be gaseous state. Okay. So now during this process energy is released. Okay. Generally electron affinity decreases down the group. The tendency to gain the electron down the group decreases, because down the group their electronegativity decreasing we studied now. So down the group tendency to gain the electron also decreases, because larger size lower electron nuclear forces, so lower will be the tendency to gain the electron. So down the group electron affinity decreases, the tendency to accept the electron will be less. So variation in a period. So from left to right as we move, we discussed that size is decreasing. If size is decreasing, effective nuclear charge increases now, and electronegativity also increases, we can say. So if this is the case, then whatever the electron we are adding, it is easily taken by that electronegative atom, because it has more tendency to gain the electron now because of its high effective nuclear charge. So now electronegativity becomes more negative left to right. It means more tendency to gain the electron. So as atomic size decreases from left to right, effective nuclear charge increases. Hence electron affinity increases in a period. So simply you can remember through this table, I mean this through this graph. So down the group decreases, across the period increases. That's it. So these are the 4 periodic properties we have discussed, and I am just generalizing everything with this particular table. So just look at here. Look at here how it is mentioned. Down the group atomic radius increases. Wherever this arrow mark is indicated, that means it is increasing that side. Okay. See here I am saying atomic radius down the group increases, increases you can say. From left to right atomic radius decreases. It means I am representing it like this. It means this side atomic radius is increasing. Okay. And you look at this ionization energy. Down the group we know ionization energy decreases. That's why I am indicating arrow mark like this. Ionization energy is more at this arrow mark. Wherever the arrow mark is side is there, that property will be more at that side. So ionization energy will be more when we move from left to right. Electron affinity is also more when we move from left to right. Electron affinity is more at bottom and less at more at top, less at bottom. Okay, remember these properties. Okay, so now what happens? These elements are more electronegative now. It means these are more electronegative, then this will be more electropositive, we can say. Okay, so as we move from this left side to right side, electronegativity increases. Electronegativity increasing means here maximum electronegativity is for halogens. Okay, and these alkali metals are now metallic, like electropositive, I can say. So whichever showing like electropositive nature, those are generally metallic character. Okay, so metals have less electronegativity or more electropositive nature. Okay, so now see this side only metallic nature is more, metallic character is more at this side, means these are more electropositive or less electronegative. Okay, or in vice versa. Okay, if they are more electronegative, those are mostly non-metallic character. They have mostly non-metallic character. So if we move from this side to here, non-metallic character increases. So these are the things I just want to add extra points also. That's why I added metallic character and non-metallic character along with the periodic properties asked in the previous exams. Okay. So this is about the first question of your classification of elements. In the next class, we will be discussing about define IE1, IE2, like first ionization energy, second ionization energy, and how can we relate them, like which is greater, which is lesser or smaller. So all these things will be discussed in the next class. Hope whatever we have discussed everything is clear. If not, you just mention in the chat box, like whichever you want, mention in the chat box. I am going to repeat the thing in the upcoming session, but by that time you should be practice it once or twice and stay confident about that. Just take the notes out of it. This presentation just I am giving so that you can make your notes on your own by looking at this discussion. Okay, right. So thanks for watching. Stay connected with our NEET World channel and you can share with your friends. Thank you.